In the previous lecture, we have discussed about swap space, and we have seen swap space use and how swap space is estimated in different operating systems. Now, in this lecture, we are going to discuss about swap space location. So we have seen that we need swap space and we name it and allocate its swap space, and we saw its use. Now the question is, where is swap space actually located? So that is what we need to know, and that is what we are going to find out in this lecture. So a swap space can reside in one of the two places. So let's see what they are. Number one, it can be carved out of the normal file system. So we have already studied about file systems, and we saw how file systems are present in our disk. Now, this swap space, it can be carved out of the normal file system. That means it can be present in the file system itself. It will be a space that will be present in our normal file system itself. So that is one of the two places where it can reside. Now, what is the other one? The second one is, it can be in a separate disk partition. So instead of it being carved out of the normal file system, we can have a separate disk partition that may be dedicated for the swap space itself. So this is another option that we can have. So we will discuss about both these options in this lecture, and we will see the advantages and if there are any disadvantages of both these options. So coming to the first one, which said it can be carved out of the normal file system. So here, if the swap space is simply a large file within the file system, normal file system routines can be used to create it, name it, and allocate its space. So here in the first option, we are saying that the swap space is carved out of the normal file system. That means it is present within our file system itself. So it will be just like a large file which is present in our file system, and then our normal file system routines can be used for creating the swap space, for naming the swap space, and for allocating the space that will be used by this swap space. So that is what happens if the swap space is just present in our normal file system itself. Now, what are the advantages of this? The advantages is that it is easy to implement. Why? Because it is present in our file system itself, and just like we treat other files, we can treat this swap space as well, and we see that creating it, naming it, and allocating space to it will be easy. So that is why we say it is easy to implement. So that is the advantage that we have with this case. Now, are there any disadvantages as well? Yes. The first disadvantage is it is inefficient. Now, why do we say that it is inefficient? Let's see. Navigating the directory structure and the disk allocation data structures take time and potentially extra disk access. Now here, since it is present in our file system itself, and we know that our file system also will be a part of our directory structure. So because of that, navigating to this, it will require navigating the directory structure and the disk allocation data structures. And this will potentially take time, and it will also need extra disk accesses. So this is the disadvantage that we have, and this is one of the reasons why we are saying that it is efficient. Now the other disadvantage we have is external fragmentation can be there, and it can greatly increase swapping times by forcing multiple seeks during reading or writing of a process image. So this can result in external fragmentation. So we have already studied about what is external fragmentation, so I'm not going to repeat that topic again. So I believe we already know what is it. Now if we are just using our swap space as a space in our file system, that means if it is carved out of the normal file system, then there can be external fragmentation that can occur here, and because of this it will increase the swapping times, and also it will increase the seek times during reading or writing of a process image, and that is the reason actually why the swap time is increasing as well. Now what is this seek? We have already studied about this when we discussed about our disk structure and the topics related to that. So there can be multiple seeks here during reading or writing of a process image. So this is another disadvantage that we have with having the swap space just carved out of the normal file system. Okay, so that was the first option that we have, and we saw that more than advantages we are mostly having disadvantages here. Okay, so now let's go to the second case or the second option that we have. So the second option we have is it can be in advantages we are mostly having disadvantages here. Okay, so now let's go to the second case or the second option that we have. So the second option we have is it can be in a separate disk partition. So instead of it being just carved out in our existing file system, we can have our swap space location in a separate disk partition which can be dedicated for swap space itself. So swap space can be created in a separate row partition as no file system or directory structure is placed in this space. So we will be selecting a separate row partition, and there will be no file system or directory structure in that partition, and it will be solely used only for the swap space. That means that partition will be dedicated only for the swap space. So a separate swap space storage manager is used to allocate and deallocate the blocks from the row partition. So in the row partition also we will be having different blocks. We know that our disk is divided into blocks. Now in order to allocate and deallocate the blocks that are there in this row partition to be used by the swap space, we are going to have something known as a swap space storage manager, and this is going to manage the allocation and deallocation of blocks from this row partition that is used for the swap space. Now this manager uses algorithms optimized for speed rather than for storage efficiency, because swap space is accessed much more frequently than file systems when it is used. Now this manager that we talked about here, it uses algorithms that is optimized for speed, because here we are concerned about the speed. Speed is our topmost priority over here rather than for storage efficiency. Why? Because swap space is something that is accessed very frequently. So if it is something that is accessed very frequently, we need to make sure that it is fast. So that is why we say that these algorithms are optimized for speed rather than for storage efficiency. So we are not concerned if the storage efficiency is very much maintained here, but we are concerned greatly about the speed. So that is why the manager uses algorithms optimized for speed. So this is what happens when we use a separate disk partition for the swap space. Now are there any disadvantages or problems with this? Let's see. So here we can have internal fragmentation. So internal fragmentation may increase, but this trade-off is acceptable because the life of data in the swap space generally is much shorter than that of files in the file system. So here we can have internal fragmentation. So in the previous option we saw that external fragmentation was a problem, but here when we are having a separate disk partition for swap space, it could result in internal fragmentation. But we are not very much worried about this internal fragmentation. Why? Because it says that this trade-off is acceptable because the data that is there in swap space is generally short-lived than that of files in the file system. Because we know that something in the swap space is not going to be there forever or for a long time. It is just going to be there for some amount of time when the swapping is taking place. So whatever data is there in the swap space is not going to be there for a long period of time. So because of that, we are not very much concerned about this internal fragmentation. And also, swap space is reinitialized at boot time. So any fragmentation is short-lived. So whenever we reboot our system, the swap space will be reinitialized. So we can say that whatever is there in the swap space is flushed or removed when the system is rebooted. So even if there is a fragmentation that has occurred in that swap space, when the system reboots, everything is wiped off and it is reinitialized again. So even if there is a fragmentation, it is not going to be there the next time the system reboots. So that is what we mean here. But one problem that we can have here is adding more swap space requires repartitioning the disk. So this is one problem that we can face here. That is, if we want to add more swap space, then we have to repartition our disk itself. Why? Because we said that we are using a separate row partition for this swap space. So there is some specific fixed amount of space that is dedicated for the swap space. And if we want to increase that, we have to repartition our disk in order to add more space to that. So that is one problem that we can have in having this separate disk partition for our swap space. So in that way, we can say that it is not very flexible in terms of adding adding more swap space to the existing one. Alright, so that was about the swap space allocation. So we have seen that there are two options that we can have. First one is we can have the swap space allocation carved out of our normal file system itself, and the second one is what we have just discussed now, that is it can be in a separate disk partition. Alright, so I hope you understood this lecture about the location of swap space. Thank you for watching and see you in the next one. In the previous lectures, we have been discussing about swap space, and we have seen swap space use, we have seen how swap space is estimated, and we have also seen the location of swap space. Now in this lecture, we'll be discussing about an example of swap space management. So we will see how swap space management is done in a particular operating system. So we are going to discuss about the swap space management in Linux. So let's see how it is done in Linux. So swap space is only used for anonymous memory or for regions of memory shared by several processes. Now in this Linux operating system, the swap space is used only for anonymous memory, which includes the memory that is assigned for stack, heap, or for memory that is used for uninitialized data of processes. And also, it is used for regions of memory that is shared by several processes. So there are memory regions that are shared by several processes. So for these things, the swap space will be used. So Linux allows one or more swap areas to be established. So in Linux, it can have one or more swap areas. And we have discussed in previous lectures that a swap area may be in either a swap file on a regular file system or on a raw swap partition. So this was basically what we have studied in the previous lecture. In swap space location, we saw that swap space can either be on the file system or it can be on a raw swap partition. That means in a different partition. So in Linux also it follows the same thing. It can be either on the regular file system or it can be on a raw swap partition as well. So it may be either of these, or it can also be a combination of these two. So both are allowed in Linux. Now each swap area, it consists of a series of 4 KB page slots which are used to hold swapped pages. Now the swap area that will be there in this Linux operating system, it consists of a series of 4 KB page slots. And what are these used for? They are used for holding the swapped pages. So we will see it in detail when we see the diagram. Now associated with each swap area is a swap map, which is an array of integer counters, each corresponding to a page slot in the swap area. Now we said that there will be a swap area here which will have page slots of 4 KB each, and associated with the swap area is going to be something known as a swap map. Now the swap map is an array of integer counters and each will correspond to a page slot in the swap area. Okay, so we will come to the details of this swap map. Once we see the diagram. Alright, so here is a diagram which shows the data structures for swapping on Linux systems. So as we said, we have our swap partition or swap file. So the swap location can either be in a separate partition or it could be a file which is present in our file system. So whatever it is, this whole area that is used for the swap partition or swap file is known as the swap area. And we see that the swap area is divided into page slots, each of 4 KB in size. So we have already seen in the previous slide that these page slots are 4 KB in size. And now here we see something called the swap map. So we said that associated or corresponding to the swap area, we are having something known as the swap map. Now we see that each page slot is pointing to a block in the swap map. Now what does this blocks mean? So here we see there is 1, this is 0, then 3, again 0, and then 1. So what do we mean by all this? So in order to understand that, we need to discuss a little more about this swap map. So let's see what is this swap map. So coming to the swap map, it is an array of integer counters, each corresponding to a page slot in the swap area, like we have seen in the diagram. Now what do those numbers mean which we saw in that swap map? So if the value of a counter is 0, the corresponding page slot is available. So those values that we saw in that swap map, they are actually counters. So as we said, it is an array of integer counters. Now, if the counter's value is equal to 0, that means the corresponding slot is available. So that means that corresponding page slot which is pointed by the counter is available. So that is what it means if the counter value is 0. Now values greater than 0 indicates that the page slot is occupied by a swap page. Now if the value of the counter is greater than 0, then it indicates that that page slot is not available, but it is occupied by a swap page. Now the question is, what do the different numbers mean? So we saw that in some it was written 1, in some it was 2, in some it was 3, and so on. Now what does these different numbers mean? So the value of the counter indicates the number of mappings to the swapped page. So that value which we see in the counter, it indicates what? The number of mappings which is made to that swapped page. So for example, a value of 3 indicates that the swap page is mapped to 3 different processes, which can occur if the swap page is storing a region of memory shared by 3 processes. Now, this is an example. So if we see that the value of the counter is 3, so it indicates that that particular swap page is mapped to 3 different processes. Now what do we mean by mapped to 3 different processes? So this can happen if the swap page is storing a region of memory shared by 3 different processes. So we already said that the swap area can be shared by different processes. So let's just go back to our diagram again. So as we understood the meaning of the swap map now, if you look at this diagram, you can understand that here the counter value is 0, which means that this page slot is empty. That means this portion of the swap area is not used and is available. And then here also we see there is 0, which means that this is also available. And here we see it is written 1, which means a value greater than 0, which indicates that it is not available, it is used, and it is mapped to one process, we can say. That is why it is 1. And here this is 3. That means that this is also not available, it is occupied, and it is mapped to 3 different processes. So that is what we just explained in the example. Alright, so this is an example of swap space management in Linux. So I hope you understood how this swap space management. what is swap area, what is a swap map, and what does the different counters in the swap map indicate. So I hope this lecture is clear to you. Thank you for watching, and see you in the in the next one. In this lecture, we'll be discussing about RAID structure. So we will be trying to understand what is this RAID and what is a RAID structure, what is it used for, and what are its advantages. So RAID basically stands for Redundant Array of Inexpensive Disk. So in RAID, what is basically done is that instead of having one single disk in our system, we attach multiple disks in our computer systems. So with the advancement of technology, the sizes of disks became smaller and also they became cheaper. So because of that, we are able to attach several disks onto our system. So as I said, disk drives have continued to get smaller and cheaper. So it is now economically feasible to attach many disks to a computer system. So RAID is a way of storing the same data in different places on multiple hard disks or SSDs to protect data in case of failure. So here is where we see the use of RAID. So this redundant array of inexpensive disk is a way of storing the same data in different places on multiple hard disks or SSDs. So for the same system, we can have multiple hard disks or multiple SSDs, and we can store our data on these multiple disks. So we can either duplicate the data or we can store it in some stripped manner, which we will discuss later. So the main advantage is that if we are having our data or the same data stored in multiple places, then we can protect the data in case of failure. So that means if one disk fails, we know that we have our data in multiple disks. So even if one disk fails, we don't entirely lose our data. So here when we say failure, we are talking about the entire loss of data where it cannot be recovered in any way. So it improves the rate at which data can be read or written if the disks are operated in parallel. So apart from this first advantage that we saw where we can protect our data, it also improves the rate at which the data can be read or written. Because if we are operating these multiple disks in parallel and we are having the data stored across these multiple disks, then we can improve the rate at which the data can be read or written, because we are not just reading or writing from a single disk, but we are doing it from multiple disks. So because of that, the rate will definitely be improved. Now it improves the reliability of data storage because redundant information can be stored on multiple disks. Thus, failure of one disk does not lead to loss of data. So here we see the name is redundant array. That means in our multiple disks, we are storing redundant data. That means we are repeating our data. We are duplicating and storing the data in the different disk. So failure of one disk will not lead to loss of the data. So with that, I hope you can understand the meaning of the full form of RAID, a redundant array. So we are storing the same data or duplicate data in multiple inexpensive disks. And why do we call it inexpensive? So we said that the disks are now cheaper, so we can economically afford to have multiple disks in our system. So in the past, RAID was used as a cost-effective alternative to large expensive disk. So in the past, this is what RAID was used for. Instead of having one large expensive disk, we can have multiple disks which are smaller and which are inexpensive, which are not too expensive. So that is why we use this term inexpensive. But today, they are used for their higher reliability and higher data transfer rate rather than for economic reasons. So in earlier days, as we said, it was used as a cost-effective alternative. In order to reduce the cost of having a large expensive disk, we were using RAID because it is a redundant array of inexpensive disk. But today it is not just used for the cost or the economic factor, but it is used for higher reliability and higher data transfer rate. So we already saw how it improves reliability because we are storing data on multiple disks, and because of that, failure of one disk will not lead to loss of data. So we see higher reliability and higher data transfer rate. So that also we saw that it improves the rate at which data can be read or written if the disks are operated in parallel. So in today's terms, instead of calling it inexpensive disk, it is better to call it independent disk because we are not using it only for the economic reasons anymore, but for higher reliability and higher data transfer rate. So because of that, the full form that is used now is redundant array of independent disk instead of inexpensive disks. Okay, so let us see a little bit about the working of RAID. So use now is redundant array of independent disks instead of inexpensive disks. Okay, so let us see a little bit about the working of RAID. So coming to the working of RAID, or redundant array of independent disk, it places data on multiple disks and allows input-output operations to overlap in a balanced way, thus improving performance. So as we already said, in this RAID, it is going to place our data on multiple disks instead of one single disk, and it is going to allow the input-output operations to overlap in a balanced way so as to improve the performance. Now, as the use of multiple disks increases the mean time between failures, storing data redundantly also increases fault tolerance. So since we are using multiple disks for storing our data, it increases the mean time between failures. So we'll be discussing about these things as we move ahead. Now, since it increases the mean time between failures, storing data redundantly will also increase the fault tolerance of a system. Now, to the operating system, RAID arrays appear as a single logical drive. So we saw that in RAID, we are using multiple disks for storing our data. But for the operating system, the RAID array will appear as a single logical drive. Now, RAID employs a technique of disk mirroring or disk stripping. Now, what do we mean by this? RAID employs two techniques. One is called disk mirroring and another one is called disk stripping. So let's see what they mean. So disk mirroring means it copies identical data onto more than one drive. So from the name itself, we can understand mirroring. It means that it is just going to copy the identical data to more than one drive. That means in multiple drives, we are having the same data stored. So it is just like duplicate data is there on multiple disks. So that is what we mean by disk mirroring. So we already saw that this can improve the reliability. Now, what is the next one? Disk stripping. So let's see what we mean by this. So disk stripping means spread data over multiple disk drives. So here we are not trying to store duplicate data, but instead we are going to have multiple disks, and the data that we have, it is going to be spread across or over these multiple disk drives. So that is what we mean by disk stripping. So these are the techniques that are employed by RAID, or redundant array of independent disk. Okay, so that was just about the introduction to RAID, what it means, what it does, and what are its advantages. So we'll be seeing more topics related. Related to RAID in the following lectures. So I hope this lecture about the introduction to RAID structure is clear to you. Thank you for watching and see you in the next one. In the previous lecture, we saw an introduction to RAID structure and we saw the basics of its working. So in this lecture, with respect to RAID, we are going to talk about improvement of reliability via redundancy. That means, how are we going to improve our reliability of the system via redundancy. So we saw that the full form of RAID itself is a redundant array of independent disk. So we see that we are having a redundant disk. So with the help of this, we will see how we are going to improve the reliability. So talking about reliability, the chances that some disk out of a set of n disks will fail is much higher than the structure, and we saw the basics of its working. So in this lecture, with respect to RAID, we are going to talk about improvement of reliability via redundancy. That means, how are we going to improve our reliability of the system via redundancy? So we saw that the full form of RAID itself is a redundant array of independent disk. So we see that we are having a redundant disk. So with the help of this, we will see how we are going to improve the reliability. So talking about reliability, the chances that some disk out of a set of n disks will fail is much higher than the chance that a specific single disk will fail. If we are considering a specific single disk, okay, a specific single disk, and if we are considering some disk out of a set of n disk, now where is the chance of failing higher? So we can definitely say that the chance of some disk out of a set of n disk failing is much higher than the chance of a specific single disk failing. So in order to make it simple, let's say that we are having 100 disks, and I am saying that the 50th disk is going to fail. So what is the probability of the 50th disk failing? The probability of a specific disk, that is the 50th disk failing, is actually low. But if I say that one among these 100 disks is going to fail, so what is the probability of that? So the probability of one among the 100 disk failing is higher than the probability of a specific single disk failing. So that is what we mean here. So for example, let us suppose that the mean time to failure of a single disk is equal to 100,000 hours. So we are saying that the mean time to failure, so when we say failure means the disk completely failing and losing all the data. So if the mean time to failure for a single disk is 100,000 hours, then the mean time to failure of some disk in an array of 100 disks will be 100,000 divided by 100. That means if we are talking about the mean time to failure of some disk in an array of 100 disks, so what will be the mean time to failure in this case? So it will be 100,000 hours, which is the mean time to failure of one disk, divided by 100 because we are having 100 disks. So this will be equal to 1000 hours or 41.66 days. So we see here that this time is actually very less. It is just like we are saying out of 100 disks in 41.66 days, at least one disk may fail. So we can put it in that way as well. Now, if that specific disk was not duplicated, or if we were not having the backup of that particular disk, then we are going to lose all the data that is present in that disk. So as I said, if we store only one copy of the data, then each disk failure will result in a loss of significant amount of data, and such a high rate of data loss is unacceptable. So if we don't have copies of the data stored in the disk, that means if we are having only one copy of each of the disk, then if we face a failure for a particular disk, then we are going to lose a significant amount of data, and we cannot tolerate such high rate of data loss. So that is one problem that we can have. So what is the solution to this problem? The solution is introduce redundancy. That means we are going to duplicate the data. We are going to store the same data in different disks, so that even if one fails, we know that we are having the data in the other disk. Thus, even if a disk fails, data are not lost. So we say data is lost only if it is lost from both the disk and it cannot be recovered. Okay, so in the previous lecture when we discussed about the RAID structure, we saw that RAID employs a technique known as mirroring. So we will be discussing about that mirroring now, because mirroring deals with redundancy. Okay, so talking about mirroring, mirroring is a technique of duplicating all the disk. So from the name itself we can understand mirroring means we are duplicating all the disk. So here we see that redundancy is being done. So this mirroring technique is simple, but it is expensive. Why is it simple? Because we just have to duplicate the disk. We are just writing the same data again and again to multiple disks. but it is expensive. Why is it expensive? Because we are writing the data into different disks, and hence we need multiple disks. So because of that, we say it is expensive. So a logical disk then consists of two physical disks, and every write is carried out on both the disks. So here we are going to use two physical disks, and they are going to be treated as one logical disk, because though they are two physical disks, we are using it to store the same data. In both these two physical disks, we are going to store the same data. So for the operating system, it is like one logical disk, and every time we write something, we have to write it into both the disks. Now if one of the disks fails, the data can be read from the other. So this is the advantage of redundancy. If we are having data stored on multiple disks, and if one disk fails, we can always retrieve or read the data from the other disk. Now data will be lost only if the second disk fails before the first failed disk is replaced. So here, when can data loss take place? Now when we say data loss, means the data is completely lost and we cannot recover it from anywhere. So that is what we mean by the data loss here. So here the data will be lost only if the second disk also fails before the first failed disk is replaced. So here we are imagining that we are having two disks, and in both the disks we are having the same data stored. Now let's say that disk 1 fails. Now we are accessing the data from disk 2. Now at the same time, we are trying to repair or replace disk 1. Now before disk 1 is replaced or repaired, disk 2 also fails. Now this is the case when data will be lost in this technique that we are following. So the mean time to failure, where failure means the loss of data, of a mirrored volume, which is made up of two disks mirrored, depends on two factors. So here we are talking about a mirrored disk, which is made up of two disks. So logically it is just one disk, but physically we are going to have two disks that are mirrored. Now the mean time to failure will depend upon two factors. Now what are the two factors? Let's see. First one is the mean time to failure of the individual disk. So this is one factor. The individual disk will have a mean time to failure. So that will be one factor. And second one is the mean time to repair. So we saw in the example that we took here, we said that the data loss will occur only if the second disk also fails before the first disk is replaced. So when a disk goes bad, there will be some time that will be taken for repairing that disk. So that also has to be taken into consideration, and that is what we mean by the mean time to repair. So the mean time to failure of the individual disks and the mean time to repair are the two factors on which the complete mean time to failure of the entire mirrored system depends. Let us suppose that the failures of the two disks are independent. So we are considering two disks here which are mirrored. That means in both the disks the same data is stored, and then the failure of the two disks are independent. That means the failure of one disk does not very long period of time. So that is the advantage that we see if we employ this technique of mirroring, which is basically nothing but introducing redundancy. So this is how we see that our data becomes more reliable by introducing redundancy. So this is one of upon the failure. If the second disk also fails, data, it may take in the previous lecture. We have talked about improvement in reliability via redundancy in RAID structures. Now, keeping in mind that we are talking about RAID structures, here in this lecture, we are going to talk about improvement in performance via parallelism. So remember that we are discussing about RAID here. So in previous lecture, we have seen how we improve the reliability of our system with the help of introducing redundancy. And here we are going to discuss how we can improve the performance via something known as parallelism. So in previous lecture, we saw that by having redundancy, what we were basically doing was we were employing a technique known as mirroring. So there what we did, we were duplicating the disks. And because of that, we were having more reliability, because even if one disk fails, we can still have the data in the other disk because the data is duplicated over multiple disks. So that is how we saw that reliability was improved. And also we have seen that the way the read requests are handled are better because the read request can be processed over multiple disks because the data is present over multiple disks. So those were the things that we saw when we employed mirroring, which enabled redundancy. So here in this lecture, we are going to talk about performance. Now, with multiple disks, we can improve the transfer rate by stripping the data across the disk. So here we are not going to do mirroring. That means we are not going to duplicate the data. Instead, we are going to strip the data across several disks. Now, what do we mean by this and how is it going to improve performance? Let's see. Let's first try to understand what do we mean by data stripping. So coming to data stripping, in its simplest form, data stripping consists of splitting the bits of each byte across multiple disks, which is also known as bit level stripping. So in the simplest form, we can say that data stripping means we are having multiple disks. So the bits of each byte will be split across these multiple disks. So let's take an example to more reliability, because even if one disk fails, we can still have the data in the other disk because the data is duplicated over multiple disks. So that is how we saw that reliability was improved. And also we have seen that the way the read requests are handled are better because the read request can be processed over multiple disks because the data is present over multiple disks. So those were the things that we saw when we employed mirroring, which enabled redundancy. So here in this lecture, we are going to talk about performance. Now, with multiple disks, we can improve the transfer rate by stripping the data across the disk. So here we are not going to do mirroring. That means we are not going to duplicate the data. Instead, we are going to strip the data across several disks. Now, what do we mean by this and how is it going to improve performance? Let's see. Let's first try to understand what do we mean by data stripping. So coming to data stripping, in its simplest form, data stripping consists of splitting the bits of each byte across multiple disks, which is also known as bit level stripping. So in the simplest form, we can say that data stripping means we are having multiple disks. So the bits of each byte will be split across these multiple disks. So let's take an example to understand this. So for example, let's say that we have a byte here, which is 11001110. Now we call it a byte and we know that one byte consists of 8 bits. So here we have 1, 2, 3, 4, 5, 6, 7 and 8. So 8 bits are there which makes up this byte. Okay, so we want to split these bits across multiple disks. So let's say how we can do that. So here, let's say that we are having an array of 8 disks. And why are we able to have this kind of array of 8 disks? Because we are talking about a RAID, which is redundant array of independent disks. So we have multiple disks like this, which we form as an array, and it is logically treated as one single disk. Okay, so we want to apply data stripping here over this byte. So what will be done is, the ith bit of each byte will be stored in the ith disk. So here we have 8 disks, and then I name them as 1, 2, 3, 4, 5, 6, 7 and 8. So let's say that these are the indexes of the disks. Now I said that the ith bit will be stored in the ith disk. So here let's say that the value of I is equal to 1. So this is the first bit. So this first bit will be stored in the first disk. So this 1 will be stored here. And then which is the second bit is again 1 here, which will be stored in the second disk. And then the third bit is 0. So the third bit should be stored in the third disk. So the 0 is stored here. And again the fourth bit is 0. So that fourth bit, which is 0, is stored in the fourth disk. And then the fifth disk is 1, which is stored in the fifth disk. And it goes on like that. So we see that data stripping consists of splitting the bits of each byte across multiple disks. So this is known as bit level stripping. Okay, so as I said, we write bit I of each byte to disk I. So that is what I just showed in the example. Now the array of 8 disks can be treated as a single disk with sectors that are 8 times the normal size and have 8 times the access rate. So 0 is stored here. And again the fourth bit is 0. So that fourth bit, which is 0, is stored in the fourth disk, and then the fifth disk is 1, which is stored in the fifth disk, and it goes on like that. So we see that data stripping consists of splitting the bits of each byte across multiple disks. So this is known as bit level stripping. Okay, so as I said, we write bit I of each byte to disk I. So that is what I just showed in the example. Now the array of 8 disks can be treated as a single disk with sectors that are 8 times the normal size and have 8 times the access rate. So as I already told you, these 8 disks will be logically treated as one single disk. And if we treat it as one single disk, and if the bits are split across this disk like this, we will be having 8 times the normal size, and it will have 8 times the access rate. So the access rate will be 8 times more than using a single disk. So this is one big advantage that we find here. So definitely from this we can see that the performance is going to be improved. So if we have a faster access rate, definitely we have a better performance. So every disk participates in every access, which is read or write. Why? Because the bits are spread across the disk. So when some data has to be accessed, so let's say that we want to access this particular byte. So all these disks will have to participate in that because these bits are spread across these disks. Now the number of accesses that can be processed per second is about the same as on a single disk, but each access can read 8 times as many data in the same time as on a single disk. So here there is something that remains the same as if we are using a single disk, and there is another factor that is much better than using a single disk. So what a day. So we see that the number of accesses that we can process per second, that is almost the same as on a single disk. So that factor remains the same. But each access can read 8 times as many data
by the help of Euler's method या रुंजा-कुट्टा method of first order. Now अब मैं आपको समझाऊंगा कि Euler's modified method कैसे हम यूज करते हैं. सो स्टूडेंट्स यहाँ पे हम देखेंगे यूलर्स मॉडिफाइड मेथड या रुंजा-कुट्टा मेथड ऑफ सेकेंड ऑर्डर कैसे समझ सॉल्व करते हैं. सो यहाँ पे क्या होता है, जो यूलर्स मेथड का जो फार्मूला होता है y n plus 1 is equal to y n plus h f x n y n, ये वैल्यू से जो भी आंसर निकलता है उसको हम यहाँ पे स्टार नाम दे देंगे. फिर हम क्या करेंगे, नया फार्मूला यूज करेंगे y n plus h by 2 f x n y n plus f x n plus 1 y n plus 1 स्टार. स्टूडेंट यहाँ से जो भी फार्मूला होगा उसको उठा के यहाँ रखेंगे, देन इस आंसर को हम क्या करेंगे, मॉडिफाई करेंगे. सो दिस इज कॉल्ड, हम यूलर्स मेथड से जो आंसर आ रहा है उसको हम वापस मॉडिफाई कर रहे हैं. सो दिस मेथड इज कॉल्ड यूलर्स मॉडिफाइड मेथड, राइट. सो क्या करेंगे, क्वेश्चन पे हम सीधा बात करते हैं. सो आपके अंदर क्या है, गिवन dy by dx is equal to x square plus y है ना, विद कंडीशन देखिए y 0 is equal to 1 है ना. आपसे बोल रहा है फाइंड y 0.02 एंड y 0.04, राइट है ना, बाय यूलर्स मॉडिफाइड मेथड. ठीक है, आप यूलर्स मॉडिफाइड मेथड से आपको क्या करना है, इन दोनों की वैल्यू निकालनी है. क्लियर स्टूडेंट. हम क्या करेंगे, सबसे पहले ध्यान दीजिएगा, जो भी हमें क्वेश्चन दे रखा है उसको हम fx y मान लेंगे, राइट, x स्क्वायर प्लस y. क्लियर. और जो कंडीशन दे रखी है उसको मानेंगे x 0 एंड y 0. सो स्टूडेंट देखो ये y की वैल्यू कितनी आ रही है, 1 आ रही है, और x क्या आ रहा है, 0. नाउ x1 कितना होगा स्टूडेंट, आपको इनकी और इसकी वैल्यू निकालनी है. तो इसको आप x1 मान लीजिए और इसको आप क्या मान लीजिए, x2 मान लीजिए. तो आपके पास जो h आ रहा है वो क्या आ रहा है, डिफरेंस कितना आ रहा है स्टूडेंट, इन दोनों का डिफरेंस, दैट इज 0.02 आ रहा है. क्लियर है. तो इसके लिए हम क्या करेंगे, सबसे पहले y1 स्टार निकालेंगे बाय द हेल्प ऑफ दिस फार्मूला. फिर इस आंसर को वापस मॉडिफाई करेंगे. क्लियर. फिर ये वाला फार्मूले से हम y2 स्टार निकालेंगे, देन फिर हम y2 निकालेंगे, और ये हमारा y1 और y2 क्या होगा स्टूडेंट, आंसर होगा. सो सबसे पहले हम क्या करेंगे, इस फार्मूला रखेंगे.
Okay, in this video, let me show you guys the Euler's method. And this right here is the numerical approach to deal with
सो पुट n इज इक्वल टू क्या रखेंगे हम 0 है ना. सो n इज इक्वल टू 0 रखा तो कितना है 0.02 का स्क्वायर प्लस हमारे पास कितने स्टूडेंट मिल गई 1. 1.0406 और इसको हम सॉल्व करेंगे यहाँ पे, यहाँ से हमारे पास वैल्यू आएगी 1.04। जीरो 8